So far, we've been working entirely in a vacuum. You've learned the formulas to calculate electrostatic fields when there's absolutely nothing in the way. But as engineers, we don't build circuits in a perfect void. We build in physical space. When an electric field moves through an empty void, it shoots unimpeded across the space. But when that same field enters a physical structure, like a semiconductor or a circuit board, it interacts with the atoms of that material. The field bends, shifts, and fragments. To solve real-world problems, we need to adapt our vacuum formulas to account for the matter that the fields are passing through. Today, we're going to figure out exactly how to calculate the electric field and flux density inside these real materials. We sort the physical world into two main categories: conductors and dielectrics. Think of an electric field in a vacuum like a sprinter on a perfectly dry track, but stepping into waist-deep water changes their movement completely. The water acts like material space, resisting energy. We measure this interaction using conductivity, sigma, and the dielectric constant, epsilon r. Conductors have extremely high conductivity, sigma much greater than 1, and relative permittivity of 1. Dielectrics are the opposite, very low conductivity, but a relative permittivity greater than or equal to 1. Recall from vacuum theory, electric flux density, D, equals the permittivity of free space times the electric field. To adapt this for physical matter, we multiply the free space constant by the material's dielectric constant, epsilon r. This maps exactly how material space responds. A higher dielectric constant means the material has a greater ability to become electrically polarized and store more charge. This is exactly why selecting the right dielectric is a critical step in modern semiconductor design. Let's apply this to a specific problem. This diagram shows an interface between a conductor and a dielectric with an epsilon r of 2. We are given an electric flux density of 2 AY nanocoulombs per square meter. Our goal is to find the electric field, E. We'll take our material space formula and rearrange it to isolate E, giving us D divided by the product of epsilon naught and epsilon r. Now we plug in our knowns. We drop the 2 times 10 to the negative 9th into the numerator for our flux density. In the denominator, we plug in our given epsilon r of 2. This table shows the standard physical constants you'll use in these problems. Instead of using the decimal approximation for epsilon naught, we'll use its exact fractional equivalent, 10 to the negative 9th over 36 pi. Using this fraction makes our hand calculations much cleaner. Watch what happens in the denominator. The 2's cancel out. The 10 to the negative 9ths cancel out. We're left with 36 pi in the AY direction, which calculates to a final electric field of 113.1 AY volts per meter. There is an easy trap to fall into. With a dielectric constant of 2, it's tempting to just divide D by 2, but epsilon r is a relative multiplier. You must multiply it by the free space constant, epsilon naught, to get the correct field. Let's lock in the 3 main rules for material space. Number 1. Conductors have high conductivity and a relative permittivity of 1. 2. Dielectrics have near zero conductivity and a relative permittivity greater than or equal to 1. 3. The modified flux equation includes both the free space and relative permittivity constants.